yesterday we spoke about filters, and we said that we could imagine that filter to be just like, we could draw a block diagram of that filter, just like the block diagrams that we've been drawing for analog systems. So there was an input into this filter, right? And that would be U. And then there was the filter itself, which is doing some kind of operation. And the output from the filter is written over there. So it's just like a normal analog system, except that it differs in one very specific way. It is not described by differential equations. So everything that we've seen so far, all of the modeling that we've done when we did Laplace transforms of things, we did Laplace transforms of simple equations or differential equations that we've taken the effort a little bit up front to linearize and write in terms of deviation variables, but the easy Laplace transforms that we did, the Laplace transforms that ended up looking like a function of S. So if you think about it, we've done, in the Laplace domain, we took something like the Laplace of dx dt is equal to minus 2x, right? And we ended up with Sx is equal to minus 2x. And we could pose that as a function of S, a Laplace transform. Now, if we had an input in there, so let's say we change this a little bit so that we have an input, we would get a U of S as well. So all of these things are functions of S. And with some manipulation, we ended up with a transfer function, right? So we moved those things, or we isolated X, and we said, okay, I can write X of S in kind of a closed form as U of S divided by S plus 2. And at that point, we had written the mechanics of the system now that is described by differential equations. Maybe those differential equations came from things like conservation laws, right? So maybe it was an energy balance, maybe it was a mass balance. But all of these things that we did Laplace transforms of that featured differential equations, we ended up with a transfer function like this. And by convention, we said, okay, let's isolate out that coefficient, and for quite a long time, a large part of this module, you've grown accustomed to seeing something like this as being a representation of a system. So you've grown used to looking at that and me saying, oh, this system is described by this transfer function. And you understood that that meant that this system would act on its inputs in a dynamic fashion. In other words, not just simple mathematics, but like a dynamic fashion, which would cause outputs. So that's the one place where we use the Laplace transform, is we used the Laplace transform to act on mathematical descriptions of systems to get a function in S that described how the system worked that we call the transfer function. A slightly different thing that we did is we also took the Laplace transform of U, right? We also did this. So we said, okay, it's also a thing that I can do. I can take the Laplace transform of the input, and I can take the Laplace transform of that input, and if that input is some known input, so maybe that's like a step input, I will write down its Laplace transform. Now, I'm just doing this recap because I want you to understand two very important things about the way that we've used the Laplace transform. We've used the Laplace transform for both systems and signals. And there's nothing in the Laplace transform. There's no way that I can look at 1 over S and know whether that came originally from a signal or from a system. Does everybody understand that basic idea, right? If I write down 1 over 2s plus 3, that could have been a function of time that I Laplace transformed, or it could have been a differential equation. Without any additional context, without any additional information, you have no way of knowing. And this turned out to be a wonderful thing. It turned out that once we did this, we could solve very interesting problems about how systems and signals interact using only the knowledge from algebra. We didn't have to reason out, oh, wait a minute, but maybe it's a tank, so that's going to be like this. We just did the math, multiplied out. We could use automated tools like SymPy, just do it, simplify, inverse Laplace transform, Bob's your uncle, there's the answer. We are now moving towards doing the same thing for discrete systems. And we'll find that discrete systems pose some interesting challenges. If we think about how to calculate the Laplace transform, so we want to do the Laplace transform. That's the first thing we have to understand. I want to say the Laplace transform gave us all these wonderful benefits, right? It got rid of the differential equations. It completely got rid of time. It allowed me to do only algebra and solve a whole lot of different questions about the dynamics of systems. Not only the basic forward simulation problem, but also qualitative calls about like, oh, if I calculate the roots of the denominator, I'll be able to calculate or determine the stability of the system without simulating, without even trying to invert the Laplace transform, right? So I'm hoping that all of those benefits can be obtained for discrete systems. But it turns out that we have to jump through some very significant mathematical hoops. I also want you, another big take home from this. So this lecture has two big take homes. The first one is the Z transform, which is where we're going to end off, is the equivalent thing to the Laplace transform for discrete systems. We're actually going to find that the Z transform is the Laplace transform with some extra substitutions to make the terms easier to handle. That's the big take home first thing. And so the things that you expect from Laplace transforms, functionally, right? Being able to calculate the Laplace transform of a system described by differential equations, that's going to be exactly equivalent to calculating the Z transform of a system described by difference equations. Okay? And being able to calculate the Laplace transform of a function of time like this, a signal, that's going to be exactly equivalent to calculating the Z transform of a signal of time, of a sampled signal of time in the discrete domain. So all of the things that we have over there, we're going to be able to do for the Z transform. Or we're hoping that that's where we're going to end up, right? And so we're going to be able to do the Z transform of one of these kind of equations. And hopefully by the end of this lecture, we'll be able to look at those equations which are now difference equations and not differential equations, and understand how I would do that. Right, so one of these, right, I would be able to do the Z transform of that. I also want to be able to do the Z transform of some signal of time. And it turns out that, just a little bit of notation here, we're only going to be able to do that if that signal is sampled. Okay, so I'm going to run through these definitions, but I want you to understand where we're going, right? So we are going to, is there something that I can do for discrete systems, differentially, for difference equations and sampled signals that has as much as possible of the same wonderful features that we have grown to love in the Laplace domain? And we're going to ask many of the same questions. Is there something that allows us to do the transform of the system, the transform of the signal, and then predict what the output will be, like we did with the Laplace transform? Is there something that will allow us to do the transform of the system and determine properties like stability, or whether we are able to build the system, so-called physical realizability? Turns out we can. And is it possible to do block diagram algebra? So in other words, we've also kind of, for free with the Laplace domain, we learned that complicated operations like convolution turned out to be simple operations in the Laplace domain. Right? So remember that if I have two blocks in series, if I have something like And you've got to force yourself to remember that that is a very hard thing to figure out if you don't use the Laplace transform, right? Because these signals, each signal is the convolution of the system with the signal in front of it. That's a hard thing. It's lots of integrals and stuff. But most of you are looking at that as like, but Carl, that's trivial. We just multiply the transfer functions together, right? It's so easy. It's only easy because the Laplace transform is so awesome, right? So now we're going to want to do something similar for sample signals. And here's how we're going to do it. So it all starts with a mathematical fiction. And that's the second take-home. That the building blocks, the underlying assumptions, this thing that I'm going to show you now, how the math works out, is not what it looks like in the wire. It's a mathematical fiction, right? What we're going to do is we're going to say, take the signal, u of t, and introduce a fictional mathematical representation of that called u star of t, which we're going to pretend, or we're just going to model as a whole lot of Dirac deltas added together. So each one of these little spiky things here, remember, these Dirac deltas, we haven't worked with them that much before. The big thing that you know about the Dirac delta is that its Laplace transform is 1, right? It's the top row of the table that by now you have very solidly committed to memory, right? So the notation for that is we're going to add together a whole lot of these Dirac deltas, and the magnitude of the delta is going to be equal to the signal at that moment in time. Okay? So if this thing is sampling every delta t seconds, the timer is clicking. So the first time is 0, the second time is delta t, the third time is 2 delta t, 3 delta t, and so on. And so the value of u of t, of u at the sampling intervals, and I'm going to have something like n going from 0 to infinity, and I'm going to have the magnitude of that delta, the magnitude of that delta is going to be the size of that u at that moment in time. Let me make that bigger. Okay, so we've got the magnitude of the delta, so there's a little peak, and now remember, the Dirac delta is an imaginary thing. We cannot ever observe this kind of signal really. Why? Because it is infinitely high and infinitely small, and yet somehow still happens to have an integral equal to that coefficient. So it's kind of a fictional thing. It's a fictional device. And this delta, so the first delta is going to have the magnitude at time 0. The second one is going to have the magnitude at delta t. The third one is going to have the magnitude at 2 delta t, and so on. But to get it to actually spike at that moment in time, I've got to shift it around, right? So I've got to translate it. And remember, I'm going to have to translate that by a certain amount of time, right? So this is like effectively I'm delaying it. And so I want you to look at that with your Laplace eyes, right? And I want you to say, I understand how I would take the Laplace transform of such a thing. I know what the Laplace transform is of the Dirac delta, it's 1. I know how to handle shifts, time shifts, delays, dead time. It's just e to the dead time s, right? And so when you think about it, if this is u star of t, it's very easy to calculate the Laplace transform of u star of t. Okay, if we understand very well how the Laplace transform works. Remember, it's a linear transform, so it will go over every element of that sum. Remember, I'm just adding lots of these terms together. So the sum, or the Laplace transform of a sum, is just the sum of the Laplace transforms. And so I can kind of imagine that the sum will go into that sigma, right? So I'm still going to have that sigma, I'm still going to have the sum, it's still going to go from n to infinity, but now I'm going to have the Laplace transform of lots of these kinds of terms, u delta t in sigma, or delta in delta t. Right? again, with your Laplace eyes, you have to remember that this thing is a constant. It is a number like 5 or 10 or 1, right? Because u is a signal, it's a function of time, but I'm only looking at the value at that moment in time. So this is just a number, it's not a function of time. Okay, so actually, that can go out of the Laplace transform, because what's the Laplace transform of a constant times something? It's just the constant times the Laplace transform. So again, I'm ending up with an even easier Laplace transform. So because that is constant, I can actually say that that's going to be and what is that Laplace transform? That Laplace transform is simply e to the minus, or actually e to the n, not minus n delta t, e to the minus n delta t s. It's the delay term, right? So that term is d in the table, right? And so we just have e to the minus ds. And so what we find is that this now has completed the Laplace transform. We now have a sum. Let's just get all of this on the screen. Sum of u delta t n times e to the minus n delta t s. Okay, so we've now calculated the Laplace transform of a sampled signal. If I know what the original signal is, yes, have I made a mistake? Because this t, that's a very good question, that t is not a time, right? This is delta t. So this is what I was trying to get at with this highlight over here, right? These things are constants. They're just numbers. They're not functions of time. There's a very common problem with understanding how this works. Those things, those coefficients there are specific values. It is the value of u at time 0, the value of u at time 1, 2, and so on, or time delta t, 2 delta t, 3 delta t, and so on. Okay? And so let's make this very specific, and you can see that if I had something like let's say I had u of t like this, right? Now remember, u of t, and let's say that I'm sampling once per second, and that my u of t is just a straightforward, simple ramp, right? Then this will be u this will be u of 0, right? This will be u of delta t. This will be u of 2 delta t. And these are now delta t, 2 delta t, 3 delta t, and so on. Okay, so that's kind of, if I had a u, that's what it would be. And these things would just be equal to numbers, right? So this would be 0. This would be 1. This would be 2 if delta t was 1, right? So given that delta t is just 1, I have numbers for all of those things, right? Like delta t is going to be 1. So 0, 1, 2, 3, 4, 5. And then u of t at each of the sampling intervals will also be 0, 1, 2, 3, 4, 5. And if I were to expand this sum, right, if I were to write the first couple of terms of that sum for that kind of input, I would end up with come now. I would end up with 0 or let's expand it, right? So u of delta t times 0 times e of minus 0 delta t s plus u of delta t 1 e minus 1 delta t s, and so on, right? That's what the sum would expand as. It's an infinite sum, but it's just these numbers, right? So it's that number, and that number, given that I know what that thing is, would be 0 times e to the whatever plus 1 times e to the minus 1s plus 2 times e to the minus 2s, and so on. Right? So by the time I've plugged in the actual numbers, by the time I know what the function is, I'm plugging in actual numbers, and I'm just expanding this big infinite sum. Right? It's an infinite sum, so it goes all the way to infinity, just like the Laplace transform went all to infinity. And we find ourselves looking at that and saying, you know what? I've done math with infinite series before. I had a whole subject where I did sums and series. And I remember there's a special rule for handling series that have this property where every next term is like a product of the previous terms. Right? So look at, why am I saying a product? Because I'm getting e to the minus 1s. The next term has an e to the minus 2s. The next term has an e to the minus 3s, and so on. So each term is being multiplied. Each, to get the next term from the previous term, I am multiplying by a factor. Is this clear to everybody? What do we call a series like that? A geometric series. Okay? And so it turns out, and we're going to make it easy, the thing that now makes this a Z transform instead of a Laplace transform. So up to now, I haven't done any Zs. I've introduced this fiction. I've said, you know what, it could be that we could do this thing with the deltas, right? You've walked with me along that route. We've calculated the Laplace transform. It looks like we end up with like these kind of infinite series. And I'm just going to propose that hopefully everybody can see it doesn't matter what the input function is. I'm always going to end up with this kind of series of e to the power something, e to the power something, e to the power something. And my hand gets really tired. So I'm going to introduce a shorthand, right? I'm going to say, let's just say that we introduce this thing called z, and that's going to be e to the delta t s. That's going to save me some writing, right? Because I'm just going to be able to say, well, that's 0 times z to the 0 plus 1 times z to the minus 1 plus 2 times z to the minus 2, and so on. So I don't have to have any s's or anything like that because all the s's are in the e's. Does that make sense? There's never going to be any s's anywhere else because all the coefficients, the things in front of the e's, are always going to be numbers. Right? They were originally functions of time, but when I did the infinite sum, I plugged in specific values for time in every one of those values. So there's no t's left here by the time I've done this. By the time I've Laplace, there's no t's. Okay? If I did it symbolically, there may be delta t's. But delta t itself is also not like time. It's a number itself, right? Like, so somewhere in the question, it'll say delta t is 0.5, right? And wherever you see a delta t, you could just as well have plugged in a 0.5. Here, right now, in front of you, is the full glory of the Z transform. This is how you do Z transforms of signals. And thankfully, you will never have to do this derivation. Because the next step, now, if this was kind of all that the Z transform did for us, it wouldn't help us that much because it takes a very long time to write down infinite series, right? So if I were forced to write down all the terms of these series every single time, I wouldn't have time for interesting things like drinking beer or having fun with my friends because I would just be writing down this infinite series all the time. So I'm going to hope that there's a way of reducing this down to a finite form. Now, turns out that we have a whole table full of already calculated pre-existing versions of these things, right? It is in the data sheet. And we are now unlocking the mysterious third column of this data sheet, right? Achievement unlocked. Okay, so we are there. We have now entered into the third row of the table. So what does this tell us? It tells us for the thing that I have on the board over there, that some clever person has said, hey, that looks like a geometric series. I know formulae that handle infinite sums of geometric series. You must have heard the story of name your famous hero. It could be Gauss, it could be Newton, but somebody who's like teacher told him, go and calculate the sum of the first 100 numbers, and he came back immediately and just gave the answer because he figured out that it was like a series. Turns out you can do the same thing with infinite series. You've done it with infinite series, and we can therefore write down the answer to this series expression directly as this. So the one that I have there, so we can actually write down that infinite series, which I have to kind of remind you, that's a polynomial. It's a so infinite series are hard to handle, and so we want to write that in a finite form, which for the numbers that I'm using now, so delta t is equal to 1, and u of t is equal to t, we end up with this number, or this expression, z to the minus 1 over 1 minus z to the minus 1 squared. If you remember that the Z transform is simply a Laplace transform of that sampled signal with this substitution, you'll be safe. If you allow yourself to imagine that the Z transform is a whole new transform, or is very similar to the Laplace transform, and you can get directly from time to Z, you'll start making mistakes. So this lecture, what I want to get you to understand in this lecture is we can do the Laplace transform of sampled signals. We can work through that and do the Z substitution, and that is called taking the Z transform of the sampled signal. And so, in short, I could write, I could actually write something like this. Now, if I were being really pedantic, I would say that what we call the Z transform of u of t, I would say, as an idea, I actually mean take the Laplace transform of u star of t and substitute z is equal to e to. So mechanically, that's what I mean. When I say take the Z transform of u of t, I mean take the Laplace transform of the sampled version, where the sampled version is now using this kind of Dirac sum, do that Laplace transform, work it out, do the substitution, and then we have the Z transform. So these are the steps, right? So this is exactly what I've got on the slide over here, right? I said I had a u of t, I got a u star of t as that sum multiplying the deltas with the values, right? I worked through that Laplace transform, I did the substitution, and now I have the Z transform of u of t. Importantly, this makes no sense if I do not sample. It only makes sense if there is a sampler somewhere. Because if there isn't a sampler and I do the Laplace transform, I won't end up with a whole lot of e to the minus delta t's. And so there will be no place for me to do my Z substitution. Okay? So you will see the textbook and you will see a lot of people. Unfortunately, it is true that within the field, people rely very strongly on the context. So you'll be doing discrete problems or you'll be doing continuous problems, and you'll need to know that when somebody writes, do the Z transform of u of t, there's a whole lot of baggage that is implied by that notation. Most importantly, and super disappointingly, I really realize this is super disappointing, there is no SymPy Z transform function. Oh. It is in some cases possible to follow this process. You'll see that there is a notebook in the repository where I actually go through for the unit step and derive the Z transform of the unit step using SymPy. So SymPy can resolve infinite series of some kinds. It can do all of these substitutions. You could do all of this with SymPy. In my experience, it's not worth it. So you can go through it and satisfy your intuition and make sure that you understand what steps are being done, but you will probably never use those techniques. You will never go from a function of time to a Z transform using SymPy. You will go from a function of time to a Z transform using the table. Now the table still is, so in other words, if I told you, so all of this stuff, you will never do. So this whole lecture, you will never apply any of these techniques, right? You will apply this. You will say, right, Carl said u of t is t. That is this line of the table. The Z transform of that function is this. So why have I actually spent a lecture explaining why this is the case? I'm explaining this so that you understand at least part of what's going on in the textbook. I've expanded a little bit on how the textbook does this derivation. I'm also hoping to close the loop on the last little bit, which is if we understand that the Z transform is a Laplace transform, you don't have to spend as much time memorizing its properties. So knowing that this is how it works allows you to infer a whole lot of properties of the Z transform. So like, for instance, that the Z transform is also going to be a linear transform. What does that mean? If I multiply u of t by a, and a is a constant, I expect to get a times the Z transform out. Why? It follows directly from these definitions. Because it's a Laplace transform of that signal, and because multiplying that signal by a works out the same way, everything still works out the same way. Now I'm going to end off, we're still going to do more tomorrow, and I'll go through a full worked example of using the Z transform to calculate outputs tomorrow. But this is the theory. I want to end off with just saying that another reason why I do like introducing the Z transform like this is so that you make the connection between Z and time shifting. So remember how we got to this. We started off with these deltas that were time shifted. Okay? So we started off with these coefficients times the deltas that are time shifted, right? We ended up with this E because of the time shift in the delta. So effectively you can say Z is like a one-time step time shift, right? That's exactly what it is. It's kind of going the wrong direction if you think about causality, but it's a one-time step time shift. That's the first thing. Z is a one-time step time shift. It's also very clear that the coefficients of the fully expanded Z transform in this form with the negative powers, each one of these coefficients is the value of the function at that time step. Right? It comes directly from this definition. We said we're going to take the Laplace transform of, right, that signal sampled at that point in time led to these coefficients. So this one for time 0 led to there. For time 1, it led to there. For time 2, it led to there. And so I can look at a multiplied out Z transform of a signal and read off the values at the sampling intervals by looking at the coefficients of Z. Now, if you didn't go through this derivation, that wouldn't be 100% as clear, right? It all links back. So if you just remember how this derivation works, you know a whole lot about how the Z transform of a signal helps us to know the values at the points. I'm going to do the Z transform of systems tomorrow. But remember, so we've done the first part now, right? We've been able to calculate the Z transform of a signal, and we know how to read the Z transform to get the values of the signal. And this is commonly known as inverting the Z transform. An important point, which is the last point here, that unlike the Laplace transform, if I give you a Z transform, you cannot tell me what the function of time was. It is not possible. Partly because most of these functions on the left-hand side of the table are not band-limited functions. And so there is no single unique function of time that goes through the points at the sampling intervals because of aliasing. The best you can do to invert the Z transform is to give me the function values at the times of sampling. Now that you can do exactly, but you can't get back, you can never get back the actual function of time. You can only ever get back the values at the sampling interval. So we now have the ability to do the Z transform of a signal. And if we understand this definition that's on the screen here, so this version of the definition of the Z transform, now you'll see if you Google this, the Z transform is technically a thing that is done on a series of numbers, right? Because it's it's a spreadsheet containing lots of different samples. So technically, this sum notation is just a way of obtaining those numbers. So another way of thinking about what the Dirac delta is doing, if you think about the delta, a specific delta is 0 everywhere except for the time when it's not 0. And so the 0, that delta has what is called the sifting property. In other words, the only thing that survives being multiplied by a delta like that is the value at that specific moment in time. Everything else gets made 0. And so this is kind of why you can imagine it being like a sampler, right? Like it's actually just taking out that exact moment in time. It's making everything else 0. And so keep in mind that that Z comes from so this definition of Z, compare that to this part here, which is the Laplace transform. It's a time-shifted delta, right? And so you can say that a Z of a particular power corresponds to the value of a signal at a particular moment in time, a number of time steps back. Does that make sense from this definition? So we have each one of these little spiky things that I've drawn here is one of these deltas, right? It's moved up, time shifted by n delta. So you can kind of say that's the 0 one, that's the 1 one, that's the 1, 2 one, and so on. And so when we do this Laplace transform, every time we see a Z, and especially this is why we favor these negative powers of Z, is because when we're talking about causal systems, we always want to be referring to the past. And so you'll see the textbook and quite a lot of control literature favors the negative power of Z form because it's got a nice interpretation. It's a back step. So Z to the power minus 1 is like take that thing and talk about the value of that thing but in the past. Or 2 time steps in the past if I raise it to another power. Okay? So once we understand that, it becomes very easy let's just go back to these machines that we were talking about the day before yesterday. Remember that we had a couple of these different filters. Here is a 2-step moving average filter, right? So this is saying I've got y of k, which is the output of that filter, is equal to a half times the input 1 time step back plus a half times the input currently. Okay? And so if you think about this definition, this idea that I've just told you, if I were to Z transform these things, right, what would that look like if I took the Z transform of that equation? Okay, so yesterday we spoke about taking the Z transform of a function, of a signal, a sampled signal. But we're still looking for, like, we also did Laplace transforms of systems of differential equations. And that worked as well. So what's the equivalent in Z? Well, this is the current, right? This is 1 time step back. And this is again current. And so when we Z transform that, I'm going to end up with y of Z times Z to the 0, in other words, 0 time steps delayed. And I'm going to end up with a half, because remember, the Z transform is a linear transform, so we expect constants to kind of fall out of the transform. I'm going to end up with u of z times z to the minus 1, because that's 1 time step in the past. Plus another half times u z. And so, once we've done this, everything is the same as it was with Laplace transforms. We can now again obtain a transfer function, knowing that the transfer function is going to be this coefficient of the input when I write it in the form. I want something output equals transfer function times input, right? And now, at this point, once I've done the Laplace transform, once I've done the Z transform and seen how the shifts work out, I can easily just solve, right? So this is just like, I would maybe, if this was a very complicated thing, I would use SymPy for that. I would just use SymPy to do the solution part for me. If it's something like this, you can kind of do it by inspection. So that's effectively now the transfer function. We have now just basically discovered the transfer function of a 2-element moving average. We've now discovered that I can write down by inspection. Really, if I have a difference equation, the Z transform basically follows from inspection. If I have linear difference equations, and the good news is I will never expect you to do the Z transform of any nonlinear differential equations, difference equations. So obviously you could go through similar steps like the whole linearization stuff, but all the ones that you're going to worry about right now will always be linear. The big ones that you really want to know about right now are the filters, right? So you want to know about these moving average filters, and you want to know about the exponential filter. So let's do the same process for this difference equation for the exponential filter, okay? So again, here we have the current value, and here we have the value 1 step in the past. And again, we're going to do exactly the same thing. If we Z transform that, we're going to end up with y of z is equal to alpha times u of z plus 1 minus alpha times y of z times z to the minus 1. Now, if you really want to, just let's say to keep things straight in your mind, initially, I call these like training wheels, right? So you can put them in just initially so that you remind yourself that actually each one of those terms is actually of the same form, but you'll tire quickly of writing down z to the 0. And you'll quickly realize that there is, like, z to the 0 is just 1. So you'll just write down a 1 eventually, right? So here we again have, but now there's a little bit of extra solution step, right? Because now we've actually got 2 occurrences of y. And so we now have to do roughly the same thing. You'll see you're using the same skills that you picked up doing transfer functions in Laplace domain. Because it's, again, once we've done this transform, it's all, again, just polynomials in Z. And so here we have y, z, and we've got to actually take out right? So I've just simplified. I've made the u to the 0s 1s, and I've collected terms. And again, we can now say that that coefficient, if we want the transfer function, we're going to end up with yz is equal to some transfer function times u of z. And that transfer function happens to be alpha over 1 minus alpha times z to the minus 1. Now, notice that I've written both of these now in the form with negative z's, because as I said, like it's pleasing to use negative powers of z because it talks about the past. But you will find it is harder to do electronic math with negative powers of z, because most of these tools want to just use normal powers. And so you'll find that the support in the scipy.signal library for transfer functions of Z assume that you're going to have positive powers of Z. Now I'm going to show you just now like how that actually works out in terms of like doing it in SymPy. But you can do all of these calculations quite successfully in SymPy. Okay, so what we find, and so the interesting thing, almost the surprising thing, is that we have so little to do. Because now if we have a transfer function and we have the input function, because these things are just Laplace transforms, finding the output, if I have a transfer function and an input, is again, it's convolution, but it's again, convolution is just multiplication. And so we just multiply the input by the output. A lot of you are like thinking, yes, but obviously that's true, but it's kind of surprising if you think about it. We multiply the input by the output, multiply the input by the transfer function, we get the output, and then we are done, right? So we have then, so for instance, one of the inputs may be something like this, right? So here we have, that is the Z transform of a ramp. And if I wanted to know what the moving average looks like when applied to a ramp, I would take this function over here, I would multiply it by that transfer function over there, and I would obtain a new function of Z, which would represent the signal, the filtered signal on the output. Now, as I mentioned, it is very important to understand that we can only ever hope to recover the values of the sampled signal at the sampling times. We cannot recover the original function of time. Okay, so if we have, so for instance, if I have my function of time here, which was a ramp, right? I've obtained 1, 2, 3, and so on for those results. Now, remember that there could have been any kind of weird function here, right? All of these functions that I'm drawing here, right, these are all functions. They're all equal at the sampling points. So that's kind of a proof that knowing the values, knowing the Z transform, because remember the Z transform just comes from knowing the values at the sampling points. How would this one transfer function, because a lot of you are thinking, I've got the table, right? What do you mean, Cole? I just go the other way. I look at the thing and I see the thing on the table, right? It's easy. How can you say I can't do that? And this is the proof, right? The proof is that all of those things have the same Z transform. Right? The straight line, the squiggly line, the one with which is like a fifth order polynomial that also goes through all of those points, all of those things have the same Z transform. So it cannot be possible to go back unambiguously. The one thing that we can do is the thing that you're saying is I can recognize that the Z transform on the right-hand side of the table corresponds to a ramp. So I can write down a function of time that will generate the same function, will generate the same values at the same points. But that's just a possibility. It's not the inverse, right? It is a function which generates the same values at the same point. And you wouldn't be wrong to add like a sign which goes through those same points, or to add another polynomial, or to add some exponential or something. You know, literally there are an infinite number of functions that go through the same points at sampling intervals. This is just a fact about math, right? So the fact that I can do that means I cannot ever unambiguously get back the original function. This is important because it's different from the Laplace transform. Laplace transforms are unique. So if I have the Laplace transform of a function, the inverse of the Laplace transform is only one thing. There's only one function that has that Laplace transform. And so that Laplace transform goes 100% identically back to that function of time. But this is different from the Z transform. So it's just important to kind of, and actually what this means to you, because I know this is what you're thinking, like what does this mean in terms of the exam? It means that if you tell me that you have inverted the Z transform and you write down a function of time, you will get 0 marks. You will need to use different words, right? And it's cool if you just remember this and you don't have any idea what I'm saying right now, as long as you avoid saying, I have inverted to a function of time, and whenever you think you want to invert a Z transform, you just say, I have inverted to the values of the function at these particular times. And if that doesn't make any sense, you write this down very carefully, right? Invert. Okay, so in other words, that is the reality. So if I have this, which we calculated as the Laplace transform or the Z transform of a ramp, if I actually take that transfer function right, so this is the Z transform of R of t, or let's say just R of t. So going that way, I end up with this, right? But if I have that Z transform, the only thing I can do going back only gives me these points. I'm not allowed to connect the points because the only thing I know is that Z transform, if I invert it, I just know what function values gave rise to that Z transform. I don't know what it looked like in between. I don't know whether Carl sneakily added some kind of sign in there that just happened to be 0 at all of the sampling points, and so it kind of changed the intermediate bits but didn't change the line. And so how do I do this inversion? That is an infinite sum, right? So it's something times z to the 0 plus something times z to the minus 1 plus something times z to the minus 2, and so on. And each one of these things is the function at the sampling intervals. And so just expanding that fraction out using normal Taylor series expansion gives you the coefficients of the infinite series. We never want the infinite series, right, because we don't have time. So we always just use a couple of elements. We say, okay, we want to just plot the first 5 or the first 20. And if that's what I want, I can just do a fifth order Taylor series expansion, and I just get the result directly. Super easy. For my money, that's the easiest way of inverting the Laplace transform if you want to do it symbolically, right? So the benefit of doing this using SymPy is that you can get those values out, even if those values are not numbers. So if I sneakily slip in something like an A or a B, right, you'll have A's and B's in those coefficients. Okay? If you just have numbers, you should just use a numeric version, which is in SciPy. The SciPy version is a lot faster. Okay, so that is everything that I expect you to know about the Z transform. So we're not going to do stability this semester. We're going to talk about the stability of these transforms only next semester. And actually, for our purposes, I'm not going to talk about physical realizability either. It fits better into next semester's work. So this is what I want you to be able to do. I want you to be able to find the Z transform of a given signal. I want you to and understanding that this means that I may give you, just like in the Laplace transform, you may need to build the signal that I give you from these basics, right? The same thing holds, right? Like if I give you a shape like this, you're going to say, oh, wait, that looks like 2 steps, one after the other, right? And so you don't have to kind of reanalyze that specifically. You can just say, you can use the same techniques that you used before with your continuous inputs, identify that as 2 steps added together, and then just use the step Z transform. Keeping in mind that this kind of shifting behavior, remember that shifting up that thing in time is effectively like multiplying by Z to a certain number of powers, right? So like the shifting part, you just do by multiplying by z to the minus n. So it's the same exact deal, same thing. So I want you to be able to know, and just keep in mind, I'm not going to ask you ever to do this kind of proof of a Z transform. I will expect you to be able to use the table to take, but I will expect you to maybe do it for complex input signals that are built from the others. So I won't just give you like, what is the Z transform of a ramp, right? Because I'm not going to give you tons of marks for reading off the table, right? Okay. I also expect you to be able to find the transfer function of any difference equation. You'll see, if you understand this one principle, which is like going 5 time steps back is equivalent to multiplying by z to the minus 5, it becomes really, really, really trivial, right? So the actual Z transform of difference equations for linear difference equations is, let's say, equivalently trivial to the Laplace transform of differential equations. The only thing you need to remember for differential equations is that d something dt goes to s times that thing. The only thing you need to remember for Z transforms is that the thing so many time steps in the past goes to the thing times z to the so many time steps minus so many time steps. That's all you need to remember. All the rest of the math is exactly the same. And I expect you to know that the transfer function is the same kind of thing that it was in Laplace, and that to find the output, you multiply the input with the transfer function and you invert. Furthermore, I expect you to have this nuanced view that inverting the Z transform is fundamentally different from inverting the Laplace transform, right? Well, Laplace transforms go both ways. If I give you a function of time, you can get a Laplace transform. I can take that Laplace transform, give it to somebody else in the class, and they will get back the same function of time. If I do the same exercise with sampled versions of a signal, you can get back different values. You can get back different functions of time, but you can't get different values at the sampling interval. So remember this. Inverting the Z transform gives only the values at the sampling interval. That's the best you can do. You can never recover the fact that there was a ramp function involved in that original Z transform. Okay. 100% complete. We've done the signals, right? We've taken that ramp function, we've calculated its Z transform. Okay, we've taken a couple of transfer functions or difference equations and calculated their equivalent transfer functions, and I've shown you in principle how to get from the result of that back to the values at the sampling points. Now, this last part, now again, if you're wondering, I'm expecting you to do this part, in other words, going from a function like this to something like that, mostly in your head and with piece of paper. That's probably the fastest way. Because you're using the table, there's not like a really easy way to do this on the computer. I'm expecting you to do the Z transform bit, just like I expected you in Laplace transforms, to take the differential equation and mentally say, okay, every time I differentiate, I'll multiply by S, to do that in your head. But I'm expecting you, if these are complicated expressions, to obtain this transfer function itself. If it's much more complicated than this, you'll probably be better off asking SymPy to solve for that transfer function, right? So, and effectively what you'll do is you'll just take this equation and solve it for y. And that'll just automatically like extract the transfer function for you, just like it was in Laplace. Then I'm expecting you basically never to do this part by hand. So in other words, inverting the Z transform is something that I do not imagine you doing by hand ever. So I never expect you to do the long division route. I never expect you to do it, and I definitely don't expect you to be able to look at a transfer function like that and know what the values will be. I expect you to type that into a computer and get the answer computationally. So just to give you a bit of guidance about like where is the computer involved in this, like I think it's almost impossible to do those problems quickly by hand.